Imagine time-lapse. A garden shed in 1885, a pharmacy pit stop in 1888, and today's turbocharged fours juggling sensors and sparks. Gasoline engines began as shaky contraptions of wood and hot tubes, yet now they deliver smooth, low-emission power through millions of tiny, controlled explosions each minute. How did small parts, rings, plugs, valves, snowball into century-spanning leaps? Buckle up, we'll start small and watch the machine reinvent itself again and again, relentlessly forward. The gasoline engine's origin story starts with an idea on paper. In 1862, French engineer Alphonse Beau de Roches described the four-stroke cycle: intake, compression, power, exhaust, a blueprint later nicknamed the Otto cycle. But turning heat into motion first went mainstream with Etienne Lenoir's 1860 gas engine, a commercially serviceable machine that proved internal combustion could power real work, even if it was crude and inefficient. The leap from concept to practical four-stroke came in 1876, when Nicolas Otto built a reliable engine on de Roche's principle, and with partner Eugen Longin, anchored production at N.A. Otto in Sia, the Cologne workshop that became today's Deutz, often described as the world's first engine factory. Then came gasoline mobility. Gottlieb Daimler and Wilhelm Maybach refined compact, high-speed petroleum engines in their garden house, work that quickly spilled into a two-wheeler in 1885 and other vehicles soon after. Finally, Carl Benz's patent motor wagons stitched the pieces together into a purpose-built automobile, validated when Bertha Benz drove it on a bold, long-distance trip in 1888. Refueling at a pharmacy and proving the concept to the world. The gasoline engine's story scales up from tiny crucial parts. Piston rings, split metal bands that expand against the cylinder wall, finally made strong compression practical, turning leaky early cylinders into efficient pressure vessels. Poppet valves, positively actuated rather than automatic, let engines breathe on command instead of by chance, enabling higher RPM and cleaner timing. Ignition left forward when magnetos and leader coil and plug systems delivered reliable, high-voltage sparks at the right instant. And Maybach's float-type carburetor solved the mixture control with a simple idea: hold fuel at a steady height, draw it through a jet as air rushes past, and keep the ratio near ideal. Each of these micro-inventions refined one slice of the cycle: sealing, breathing, sparking, and mixing, until the aggregate engine finally behaved like a precise machine. With fundamentals in place, mobility arrived. Compact, fast-revving petroleum engines from late 19th century workshops could be tucked into bicycles, boats, and carriages. Carl Benz's purpose-built three-wheeler integrated the four-stroke with a lightweight frame and belt drive, proving that a gasoline engine could power a practical vehicle rather than an experiment. Just a generation later, the electric self-starter replaced hand cranks and widened the market to anyone who could turn a key. Overhead valve layouts lifted the valves into the head, shortening the gas path and improving breathing without exotic parts. The cumulative effect was decisive. Starting became easy, drivability improved, and engines grew smaller and smoother while delivering more power per liter. As speeds rose and expectations sharpened, fueling and airflow saw a new wave of ideas. Aviation's quest for power at altitude pushed superchargers and better fuels, lessons that filtered into road cars. Mechanical fuel injection arrived in niche applications, metering fuel with cam-driven pumps and nozzles rather than relying on vacuum draw. The advantage was accuracy: precise doses at the right moment, steadier torque, and improved throttle response. Even when injection targeted the intake ports rather than the chamber, atomization improved and mixtures stayed closer to ideal across conditions. These systems were costly and complex, but they foreshadowed a future where mixture control would be a job for instruments, not intuition. The regulatory turn of the 1970s forced combustion to grow up fast. Electronic fuel injection replaced mechanical metering with sensors and a control unit that could adjust pulse width in real time. Closed-loop feedback using an oxygen sensor kept mixtures near stoichiometric, where the three-way catalyst can simultaneously oxidize carbon monoxide and hydrocarbons while reducing nitrogen oxides. Suddenly, chemistry joined mechanics as a co-equal partner. The exhaust stream itself became a second stage where leftover pollutants were cleaned before exiting the tailpipe. Onboard diagnostics standardized fault detection, and microprocessors made minute-by-minute tuning normal. The gasoline engine evolved from a mostly mechanical contraption into a network system of sensors, actuators, and aftertreatment. With male emissions under control, engineers chased efficiency and flexibility. Turbocharging returned as a mainstream tool. A turbine harvesting exhaust energy to compress intake air, yielding more oxygen per stroke without adding displacement. Variable valve timing and lift widened the torque curve, phasing camshafts at low RPM for tractability and switching profiles up high for power. Knock sensing let engines creep closer to the detonation threshold safely, unlocking higher compression ratios and aggressive spark maps when conditions allowed. Friction reduction, cooled exhaust gas recirculation, and sophisticated combustion chamber shapes nudged thermal efficiency upward. The overall result was paradoxical but real. Smaller engines that felt larger, using less fuel to do the same work. In the current era, integration rules. Direct injection sprays fuel straight into the chamber, enabling stratified charge strategies at times and cooler, knock-resistant operation. Paired with downsized turbos and precise ignition control, modern gasoline engines deliver diesel-like torque at everyday revs. To manage particulate matter from direct injection, gasoline particulate filters trap and periodically burn off soot within a ceramic honeycomb, often packaged with the catalyst. Hybridization layers a motor and battery onto the engine, letting electronics shift load to the engine's sweet spot and coast or crawl on electric power when that's more efficient. Brake thermal efficiency nudges past 40% in specialized hybrid cycles, while exotic mechanisms like variable compression linkages let the same hardware run a frugal high compression loop under light load and a detonation-resistant low compression loop under boost. Each step is small in isolation, but together they form a system that is quieter, cleaner, and more adaptable than the pioneers could have imagined. An engine that constantly measures itself, learns from the last cycle, and adjusts before the next explosion even begins. After the methodical march of valves, rings, and carburetors, some pivots came from pure scrappiness. In Constat, Daimler and Maybach hit prototypes in a garden house workshop so unassuming that police suspected counterfeiting, not engineering. Their grandfather clock engine revved far higher than the lumbering industrial motors of the day, unlocking lightweight vehicles instead of stationary machines. A single road trip turned curiosity into credibility. In 1888, Bertha Benz quietly set off with a patent motorwagen, buying Ligerin at a pharmacy, unclogging a fuel line with a hat pin, and lining brake shoes with leather at a cobbler. It was part engineering test, part public demo, a proof that fueling, fixes, and everyday journeys were possible. Then there are ideas that arrive decades early and wait for their moment. In the 1950s, tiny German cars ran mechanical direct injection, precision fueling long before sensors and ECUs made it cheap and reliable. The concept was sound. Materials, manufacturing, and computing simply had to catch up. When they did, modern GDI reshaped efficiency and power. The 1970s forced a rethink from two directions at once. Oil shots demanded frugality, and clean air rules required chemistry. One path, Honda's CVCC, met limits with clever combustion. The other paired oxygen sensors with three-way catalysts to make the exhaust a second-stage reactor. Even turbo stumbled early, fluid injection quick fixes, before returning as the backbone of downsized efficiency. Today's gasoline engine is a coordinated orchestra of sensors and software. Direct injection places fuel precisely in the chamber. Turbochargers reclaim exhaust energy to cram in more air. Wide-band oxygen sensors keep mixtures right where catalysts work best. Gasoline particulate filters quietly trap soot from GDI, while cooled EGR, NOx sensors, and multi-hole injectors tame heat and detonation. The result is paradoxical. Smaller engines that feel bigger with cleaner exhaust than most drivers imagine. Hybridization reframes the engine's job. In parallel and series parallel systems, the motor handles low-speed grunt and stop-go inefficiency, letting the engine loaf at high-efficiency load points or shut off entirely. Atkinson-Miller timing, low-friction internals, and clever cooling deliver brake thermal efficiencies once considered diesel territory, while 48-volt mild hybrids add seamless start-stop, torque fill, and coasting without the cost of large batteries. New frontiers are already on the road. Variable compression mechanisms shift ratios on the fly, high for sipping, low for boosting, expanding the efficiency window. Spark-controlled compression ignition, SCCI, blurs the line between gasoline and diesel combustion, chasing lean, stable burn with minimal knock. Camless concepts promise per-valve freedom for breathing strategies software can remix in milliseconds. Looking ahead, expect deeper electrification, ubiquitous GPFs, and tighter integration with transmissions and thermal systems. E-fuel pilots hint that legacy fleets might decarbonize without scrapping hardware, while performance niches keep refining low-carbon, high-output ICEs. The gasoline engine's future isn't singular, it's a spectrum, leaner, smarter, and increasingly partnered with electrons. From the shed-built grandfather clock to variable compression, sensor-dense hybrids, the gasoline engine's arc is really a chain of tiny fixes compounding into outsized leaps. Rings sealed compression, valves learned to dance, sparks arrived on schedule, fuel metered itself, chemistry cleaned the tailpipe, software stitched it all together. It didn't win by a single breakthrough. It survived by 1,000 modest ones, stacked in the right order. And now, with electrification rising and carbon budgets shrinking, the engine hasn't vanished. It's changing its job description, sharing loads with motors, sipping instead of guzzling, aiming its power at the moments humans still crave mechanical response. Maybe its last chapters are about companionship rather than dominance. Hybrids, e-fuels, niche performance, resilient backup, or maybe a new combination of materials, controls, and renewable fuels will turn another corner we can't yet see. So, what do you think the next leap looks like? And will it be the engine's encore or its epilogue? I'm curious. What era grabbed you most? The scrappy 1880s? The emissions moonshot of the 70s? Or today's sensor-driven hybrids? Drop your pick and why. If there's a chapter you want next, turbos, fuel injection, variable valve timing, or camless dreams, say the word. If this deep dive clicked, passing it to a friend or tapping subscribe helps me keep building bigger stories. And if you're in the mood to keep rolling, there are more engine evolutions and tech timelines waiting on the channel. Pick any video that catches your eye and see how another small idea reshaped the machines around us.